Hello friends, so today we are going to solve questions from the year 1990, and there are total 3 questions from year 1990. From the year 1991 we are having 2 questions, and from the year 1992 the number of questions are also 2. Therefore, in totality there are 7 questions. So first question, it was asked in the year 1990, and it states that 7 capacitors, each of capacitance 2 microfarad, are connected in a configuration to obtain an effective capacitance of 10 by 11 microfarad. Which of the following combination will achieve the desired result? So the capacitors are connected in all these options, in series as well in parallel, and we know when the capacitors are connected in series, the equivalent capacitance is given as, suppose there are 2 capacitors, it will be C1 multiplied by C2 and C1 plus C2. And when they are connected in parallel, the equivalent capacitance will be equal to C1 plus C2. In this case, we want that our equivalent capacitance should be equal to, effective capacitance should be equal to 10 by 11 microfarad. Okay. And it is given that we have a total 7 capacitors and each having a 2 microfarad. Okay. So from series combination, if we substitute value of 2 capacitance, we can get that the series capacitance is going to give us a value of 1 microfarad. Okay. When we have each value is equal to our 2. And obviously the other 5 will be connected in parallel, so that we get them as a, because that will be giving us a 10. Okay, so this will be C1 plus C2 and up till C5, and this will be coming as our, one second, yeah, so that will be coming as 10. So it means our net equivalent capacitance will be equal to our net equivalent capacitance because of series plus net equivalent capacitance because of the parallel. And sorry, not my mistake, this will be our, we can write this as, yeah, so this can be written as multiplied by and divided by our series and plus C parallel. And we have our C series is our 1, C parallel is our 10, and this comes as 1 plus 10, giving us 10 upon 11 microfarad. So here we get, this will be coming as 1 microfarad, and the parallel combination will be coming as 10 microfarad. So option number A is the correct option. Option A is correct. Next question, and it states that it was also asked in the year 1990, and it states that 3 concentric spherical metal shells A, B and C of radii A, B and C, small a, B and C, such that the order is given as C is having a highest radii, then B, then it is A, have a surface charge density of plus sigma, minus sigma as well as plus sigma respectively. So we have two questions based on this description. First one is find the potential of the 3 shells A, B and C. And part B, it states that if shells A and C are at the same potential, obtain the relationship between A, B and C. So we are given charge in the formation of their surface charge density. So let us draw an approximate figure for that. So we have our, so this is shell A having a radius of A. Then we have our shell B having radius of B. And finally we have our shell C. And having a radius of C. So this is our shell C. And their respective charge density for shell A, it is given as plus sigma. For shell B, it is given as minus sigma. And for shell C, it is once again given as plus sigma. And we can find out the charge on shell A, B as well as C, because in terms of their charge densities. So you can say that charge on shell A, let us call that as QA, which will be equal to 4 pi A square multiplied by its surface charge density. Then we can find for B, let us call that as QB, and that will be equal to 4 pi B square, and this is minus of sigma. And then we can write for C also. C, let us call that as QC, will be equal to 4 pi C square, and then it multiplied by sigma. And we are supposed to find out the potential of three shells. It means potential of A, potential of B as well as potential of C. So let us start with A. So you can see potential of shell A. Let us call that as our VA. And VA, we have to remember that this shell A is inside the shell B as well as shell C. So you can say that shell A lies inside B and C. So therefore we can say that our VA will be equal to 1 upon 4 pi epsilon naught, and this comes as our QA divided by A plus QB divided by B plus QC divided by C. Now we substitute value of QA, QB and QC, and we get this as 1 upon 4 pi epsilon naught QA was our 4 pi A square sigma upon A, and QB was our minus, this is minus 4 pi B square sigma upon B, and finally is our plus 4 pi C square sigma upon C. And we can cancel out our square terms. So we can say A go by square, B goes by square, and C goes by square. And we can take common as 4 pi sigma. So we can write this will be equal to, we get this 4 pi upon sigma divided by 4 pi epsilon naught, and this comes as A minus B plus C. And here 4 pi and 4 pi cancels out, therefore we get our VA is equal to sigma oblique epsilon naught, this is A minus B plus C. So this is potential of the shell A. Now we come to the potential of shell B. So for shell B, let us call that as a VB, and we have to remember that B is outside A but inside C. So we can say B is outside A and inside C. Therefore, we can write that our VB will be equal to 1 upon 4 pi epsilon naught. First is our QA divided by B plus QB divided by B plus QC divided by C. And once again, we already know value of QA, QB and QC. We substitute them and we get 1 upon 4 pi epsilon naught. QA was our 4 pi A square multiplied by sigma divided by B minus 4 pi B square sigma divided by B plus 4 pi C square multiplied by sigma divided by C. And here we can say this B and square goes away, C and square goes away, and we can cancel out our 4 pi throughout. So this 4 pi, 4 pi, 4 pi and 4 pi cancels out, and we can write taking sigma as common. So this comes sigma upon epsilon naught. It comes as A square upon B minus this is our B and plus C. So this is our VB. Now we come to our shell C. Shell C, let us call that as VC, and shell C, it lies outside shells A as well as B. Okay. You can say C lies outside A and B. Therefore, we can say our VC will be equal to 1 upon 4 pi epsilon naught. We have this as QA upon C plus QB upon C and plus QC upon C. We substitute QA, QB and QC, and we can write this as 1 upon 4 pi epsilon naught. QA is our 4 pi A square sigma upon C minus 4 pi B square sigma upon C plus 4 pi C square C and multiply by sigma. And here this 4 pi is going to cancel throughout and C square goes by this square. Sigma we can take common, so we get our VC will be equal to sigma upon epsilon naught. We get this as A square upon C minus B square upon C plus C. So this is the potential because of the shell C. And in the B part, it states that the potential at A as well as potential in C are equal. So for part B, it states that potential at A is equal to potential at C. We substitute the value sigma epsilon naught, and we have this as A minus B plus C is equal to sigma epsilon naught, and C is our A square upon C minus B square upon C plus C. And the sigma epsilon naught cancel out, and this C and C is also going to cancel. This C and this C also goes away. Therefore, we can write this as taking C as LCM. So this comes as A minus B is equal to A square minus B square upon C, which we can write A minus B into A plus B divided by C. And this A minus B and A minus B cancel out. Therefore, we get that our A plus B upon C is equal to 1, which gives us that our A plus B is equal to C. So this is the relationship between A, B and C when potential of A is equal to potential of B. Next question. We are given that we have a circuit, and in this circuit it says that it was asked in the year 1990. It states that in the given circuit E1 is equal to thrice E2 is equal to thrice E3 and is equal to 6 volt, and R1 is equal to 2 R4 is equal to 6 ohm, and R3 is equal to twice R2 is equal to 4 ohm, and C is equal to 5 microfarad. Find the current in R3 and the energy stored in the capacitor. So basically it should have mentioned that under steady state condition, but in this question it is not mentioned. So we already know that for, or we can say under steady state condition, our capacitor, that is our C, is going to behave as an open circuit. So the capacitor will be open circuit, and if capacitor is open circuit, then we can say that no current will flow through R1. So there will be no current flowing through this R1 resistance. No current through R1. and we can just draw the circuit, equivalent circuit, when this capacitor will be acting as open circuit. And so we are going to have a battery source, and here we are going to have another battery source, the resistance, and here also resistance, and then there will be another battery source, and we have resistance. So we have our E1, E2 and E3, R2, R3 and R4. And let us name all the nodes. We are going to use our Kirchhoff voltage law. So this is our A, B, C, D, E, F and G. So from E1, let us suppose the current that is flowing is our I1, and at node B, let us suppose the E3 is giving a current of our I2. Then through our R3, we are going to have two currents, that will be I1 plus I2. And at node F, it will be divided into two parts. So we are going to have GF will be obviously our I1, because the current outgoing from the battery should be equal. So we have this I1, and obviously the other current will be our I2, that will be flowing through as R2, and the current that is incoming to E3 will be our I2. And we are given that E1 is our 6 volt, so this is our 6 volt, and E3 is our will be equal to, I think, it should be 2 here. Yeah. So E2 will be equal to 2 volt and E3 will be equal to 3 volt. Now we can easily use our Kirchhoff voltage law, and first of all let us consider the loop, that is our A, B, F, G, A. So we can say Kirchhoff voltage law, and the loop is our A, B, and we have this as F, G and A. And let us draw this loop. And in this loop there is only one resistance, that is we have our E1 which is our 6, and we have our R3, and the current through here is our I1 plus I2, and current is flowing from right to left. So obviously right end will be positive and left end will be negative, and we can just take the directional loop same, because it doesn't matter. So we can say, if we start with the potential, that is, so for E1 that will be over minus of E1, because that is a fall in potential. So we can say minus of 6, and this comes at plus, and here we have a, sorry, not plus but minus, and that will be equal to our fall in potential, that is of R3 multiplied by I1 plus I2, and their summation will be equal to 0. Let me check, this is the correct one. Yes, so this is plus minus, no, looks good. We will just re-verify that later on also, but for the time being it looks good. And the second, we are going to take loop B, C, D, E, F, B. So we have our KVL, and the loop is our B, C, D, E, F, and B. Once again, we can draw its equivalent circuit. So we have a E2, then we have our R2, and we have our R3, and a battery source, that is our E3. This is our E2, E3, and finally we have our R4. And the current through R3 is our I1 plus I2, current through R2 is our I2, and current through R4 is also our I2, and direction will be plus minus, plus minus, plus minus. And we can just take the loop. Let us take the loop in this direction. Okay, and we can write the equation is our plus E3 was our 3, so E3 was our 3 and E2 was our 2. So this comes in the rise in potential, that will be plus 3 minus, and this will be R4 multiplied by I2, and this will be minus R3 I1 plus I2, and we have this is minus of R2 multiplied by I2, and this is minus of 2 is equal to 0. Okay, I think all the source, let me check the directions are the correct one. E1 is correct, E2 is correct, and E3 is also correct. That looks good. And we already know that the value of R3 we can substitute here. So from here we can get that our R3, let me write it here, so get R3 I1 plus I2 will be equal to minus of 6. So we substitute it, we get this as 3 minus R4 I2, this comes as plus of 6 minus of R2 I2 minus of 2 is equal to 0. And I2 and I2 is common, so this comes as 6, and this is 6 plus 3 is 9, 9 minus 2 is our 1 second. So we get this as I2 is common, or you can say minus I2 is common. So we get this as R2 plus R4 will be equal to minus 6 plus 2 minus of 3. Okay, so R2 and R4 is our 3 plus 2. 1 second. Yes, so R3 is our 2 and R2 is also our 2. So both R1 is our, let me calculate them here. So I can see my R1 is equal to 3 ohm, R4 is also equal to 3 ohm, and I have this R3 will be equal to 2 ohm, and my R2 will be also equal to 2 ohm. So this comes as 3 plus 2. So I get this as minus of I2 and R4 is 3 and R2 is 2. So this comes as 2 plus 3 will be equal to, this will be equal to our minus 9. Minus 9 is our minus of 7. Minus and minus will cancel out. So we get our I2 is equal to 7 upon 5. If I2 is 7 upon 5, one second. Sorry, this is rise in potential, so it has to be plus 6, not minus 6, my mistake. Because we have taken the loop is in this direction. Yeah, so this is plus of 6 and this is okay. So we come this as will be our plus of 6 here, and so we can write this will be equal to our minus of 6, and here it will be our minus of loop is in minus of 2. This looks good. Plus of 3, it looks good. So this comes as 6 plus 2 is our 8. Yes, sorry for the mistake. And this comes as plus, plus and minus, and this will be equal to our minus, and this is our 6 plus 2 is 8, and this comes as our 5. I think I missed something. Doesn't look. So this is plus minus fall in potential. This is minus R for R2. This is R3 fall in potential, and this is our I2. This is also correct, and we have our minus of 2. This looks correct, and this is our plus of 3. Once again, same mistake. We have rise in potential, that is plus of 2. Plus of 2, and this comes as minus of 2. So this will be equal to our 1 finally. Therefore, we get our I2 is equal to our minus 1 upon 5. And let's correct now. And we can use, let us solve this as equation number 1 in order to find out I1. So we can say from equation 1 we have our R3 multiplied by I1 plus I2 is equal to 6, and our R3 is equal to 2. So we get from here I1 plus I2 is equal to 6 upon 2, which comes as 3. And I2 we found out minus 1 upon 5. So we can say our I1 will be equal to 3 minus of I2. We substitute the value, we get our I1 is equal to 3 plus 1 upon 5. And this will be coming as 16 upon 5. One second. R3 is 4 ohm. R3 is 4 ohm. Okay. R3 is 4 ohm. 4 ohm. Here goes 4 ohm. And this comes as 6 by 4. This also comes as 6 by 4. So we get that our I1 will be equal to, we can say 20 is our LCM, and this comes as 30 plus 4, that is 34 divided by 20. And we can just, this will be coming as 10 and this comes as 17, which gives us that our I1 is equal to 1.7 amperes. So we need to find out the current through R3, and the current through R3 is our I1 plus I2. Therefore we can say that current through R3 is equal to I1 plus I2, and our I1 plus I2 is equal to 6 by 4, because we already found it here, that is our 6 upon 4. Or we can say, we can just cancel it. This goes by 2 and this goes by 3. So we get this current will be equal to 1.5 amperes. This is the current through R3. And we need to find out the voltage, the energy stored in the capacitor, which is half CV square. And we need to find out the potential difference across the capacitor. Potential difference across the capacitor. And the capacitor will be acting as an open circuit, and therefore we can say we are only interested for the capacitor will be only this circuit part. No current is flowing, so this R1 is not of the importance. We are only interested in our E2 as well as R2, that is a voltage drop, because I2 we already know. So we can just draw the approximate circuit for that. This is our open circuit, and here ideally we should be having a resistance, that is our R1, but as such no current is flowing, so we are just going to ignore it. And here we are having a voltage source, and here we are having a resistance that is given to us as R2, and this is our E2, which we just found out is our 2, and the current through R2 is our I2, and I2 we found out I2 was equal to I2 is minus 1 upon 5. Okay, so here we have our 1 upon 5, that is our I2. Therefore, this was our point E, and we were having E, F and G. So this point was our F and this point was our G. So we can say that our VE, that is a potential at point E, let us call that our VE, and at G let us call that our VG. So we can say our VE, and this is our fall-in potential, that is minus of 2, and this will be our minus and this will be plus, so that will be our, you can say, rise in potential, but the current is negative, we have to remember it. So this is rise in potential, this comes as plus, and here we have our R2 and multiply by minus of I2, and then we are going to have it as will be equal to VG. So we can write our VE minus VG will be equal to, this comes as 2, this will plus R2 multiplied by I2. And now we simply substitute the values. We this have as 2 plus, and we get this as 1.5, that is 0.5 multiplied by 2. So we get this as 2, and this is 1 by 5. We have this as 1 upon 5, so this comes as 2 plus 2 upon 5, and that will be equal to 12 upon 5. And that will be equal to 2.4 volts. Now we can easily find out the energy stored in the capacitor. Energy stored in capacitor, that is of half CV square. We get this as half multiplied by 5 into 10 to the power minus 6, and we just found out is 2.4 multiplied whole square, and this comes as approximately 1.44 into 10 to the power minus 5 joules. So this was our, you can say, this particular question. Okay, next question, and it states that it was asked in the year 1981, and it states that a parallel plate capacitor of plate area A and plate separation small d is charged to a potential difference V, and then battery is disconnected. A slab of dielectric constant K is then inserted between the plates of the capacitor so as to fill the space between the plates. If Q, E and W denote respectively the magnitude of charge on each plate, the electric field between the plates after the slab is inserted, and the work done on the system in the question in the process of inserting the slab, then we have to find out what will be the value of Q, electric field, as well as the work done. So basically we have two situations, and in first part there is no dielectric, and suppose the capacitance is ever C, then this value of C will be equal to epsilon naught A upon D. Okay. And in the second part, when dielectric is inserted between the plates, so we have some kind of dielectric. Now in this case, the capacitance C, let us call that as C prime, will be equal to dielectric constant is given as K, and that will be equal to epsilon naught A multiplied by D. So these are the two situations here. So this is our initial, and this part is our final. But during this entire process, the charge, because the battery has been disconnected, the charge remains constant. So from here we can just write it that the charge on the plate remains constant. The charge on the plates remain constant. Therefore, we can say our Q will be equal to, let us call this as C naught, initial capacitance. So this will be our C naught multiplied by the potential, that is our V. Okay. And we substitute value of C naught, so this comes as our epsilon naught A D and multiply by V. And suppose the final potential is V prime. So here this V is the initial potential difference, and let us say that the final potential difference, or we can say new potential difference, final or new potential difference, let us suppose if given as V prime, then this V prime will be equal, because charge will be same, so this comes as Q upon C prime. C prime we just found out, so we can say this will be equal to, we can substitute value of Q, and Q will be equal to our epsilon naught A multiplied by V whole divided by d, and c prime is our k, and this our epsilon naught a upon d. Therefore this epsilon naught a and epsilon naught a d cancels out, so we get this as v upon k. Therefore from here we can say new potential difference v prime will be equal to v upon k. Now we can easily find out the electric field. So we can say our electric field, that is our E, will be equal to v prime divided by d, and v prime is our v upon k, so we get this v upon k multiplied by d. So this is our electric field. So electric field is v k d. So option C is the correct one. C is correct. And the charge we also found out. Charge was our option A is the correct one for the charge. So from here we can say option A is correct. Option A is correct. Finally, so option B will be obviously wrong, and now we have to find out the work done. So work done is nothing but a change in the energy, that is electrostatic energy. We can say our work done that is our W is equal to change in electrostatic energy. Change in electrostatic energy. So we substitute the value, we get our W will be equal to, we can say we have this as 1 by 2, and this is a C naught V square minus, and the final was our C prime and V prime square. And we can just substitute the values. We get this as our half C naught, we already know is our epsilon naught A d V square, and this is minus half C prime, also know is our K epsilon naught A d, and V prime is our V upon K, and this is our whole square. So we can take common, so we get our work done will be equal to, we have a half epsilon naught A upon d, and we can also take our V square also as common. So this comes as 1 minus, this is K upon K square. This square goes with K. So we get our work done W is equal to half epsilon naught A d V square 1 minus 1 upon K. So this is our work done. And option number D is also correct. Option D is correct. Next question. And it states that we have a, it was asked in the year 1991, and it states that two fixed charges minus 2q and q are located at points with the coordinate minus 3a 0 and plus 3a 0 respectively in the xy plane. And based on this description, we are having two questions. Sorry, three questions are there. First states that show that all the points in xy plane where the electric potential due to two charges is 0 lie on the circle. Find the radius and the location of its center. Give the expression for v of x at a general point on the x-axis and sketch the function v of x on the whole x-axis. And the third is, if a particle of charge plus q starts from rest at the center of the circle, show that by a short quantitative argument that the particle eventually crosses the circle. Find its speed when it does so. So first part, it says that we have to find out the locus of where this electric potential is 0 because of the two charges. Okay. Or here it is said that we have to prove that that locus is basically circle. So let us draw an approximate figure. So we are given the position of the charges. This is x-axis, y-axis. So this will be our minus x. Let us call this as plus, and this will be our minus of y. And we have this as a origin. So we have a charge of minus 2q at minus 3a0. This is our suppose minus 3a0, and here charge is our minus 2q. Let us call this as point as a. And other point, let us call this as point as b. It is given as plus 3a and 0. And the point P is given in xy plane, and let us suppose that point is somewhere here. This is point P, and its coordinate is given as x and y. Let us join this point P. And here charge is given as plus q at point B. So we are given in the question that the electric potential due to the charges should be equal to 0. It means electric potential at P should be equal to 0. That is the basic question. So we say that potential due to, sorry, it is minus 2q and plus q at potential due to minus 2q and plus q at P is equal to 0. Therefore we can say that potential due to minus 2q should be equal to potential due to plus q. And or we can also say, it's much more convenient if we say, if we add them, that should be equal to 0. Okay. And we can find out this easily. Potential due to minus 2q at point P. And let us draw this perpendicular. So this will be our height, will be our y, and this coordinate will be our x. Therefore the distance from Let us call this point as C. And this total distance will be equal to over 3a plus x, and this distance will be equal to 3a minus of x, okay, distance of this C point. So this distance, our AP, will be equal to square of y plus square of 3a plus x and its square root. So we can say our AP will be equal to, or rather we can say AP square will be equal to our y square 3a plus x whole square plus y square. And similarly we can say that our PB square will be equal to, this comes as 3a minus x whole square, and this will be our plus y square. So let us remove the square terms, and we can say square root as well as here also square root, because these are nothing but right angle triangles. This is also right angle triangle and this is also right angle triangle. Okay, now we can easily find out the potential. So this comes as our minus k 2q and divide by the distance, which we found out as our 3a plus x whole square plus y square square root, plus this comes as k and this is our plus q, and this comes as 3a minus x whole square plus y square, and square root is equal to 0. And obviously k and q cannot be equal to 0, so we can just write it that we get this equation, this will minus and minus minus will cancel out, so we can write this will be equal to 1 upon, sorry, not 1 upon, 2 upon 3a plus x whole square plus y square square root is equal to 1 upon 3a minus x whole square plus y square and its square root. If you cross multiply them, we get this will be equal to twice, and this is our 3a minus x whole square plus y square square root is equal to 3a plus x whole square plus y square and its square root. Now we can just simply square them. So we get from here that our 4 will be equal to 3a minus x square plus y square is equal to 3a plus x whole square plus y square. And this is now quite simple. We just open it, and it will be a little bit complicated, lengthy rather, to solve it, but ultimately it will be coming like a circle, and the equation will be x minus 5a whole square plus y minus 0 whole square is equal to 4a whole square. So obviously this is nothing but equation of a circle, equation of a circle, and the center will be 5a comma 0, and radius will be 4a. So therefore part A we have sorted out, and we can just draw the required radius is our 4a, and center is given to us as 5a. So this is our 5a, 0. So we can say that the circle is something like this. And radius will be of 4a. So the total distance is of 5a, and radius means that this point will be coming as a, 0, and this point will be coming as 9a, 0. So this will be the circle. And in the part B, it says that find the expression for v of x, where x is any point on the x-axis. Okay, we need to find out the expression for the potential. So we can say the potential will be equal to potential due to q as well as the potential due to minus 2q. So we can say V will be potential due to Q plus potential due to minus 2Q. And we can simply substitute the values. Because we are only talking about a general point, so we can say this is 1 upon 4 pi epsilon naught, and we get this as will be equal to q upon this is our 3a minus x whole square plus y square, and 1 upon 4 pi epsilon naught we can take as common, and this will be minus 2q divided by 3a plus x whole square plus y square. And so we can just define this particular equation, because we need to plot the graph, and because if the points at x is equal to 3a or x is equal to minus of 3a, this potential will be equal to as, you can say, not defined, it will be basically coming as infinity. So we can say on x-axis potential will be undefined, defined at x is equal to 3a as well as x is equal to minus of 3a. So we are going to take you can say different values of x and find out how the potential is going to change, except these two values, because it will be infinity at these two values. Okay. Therefore, for the first, let us consider that our x is greater than minus of 3a but less than plus 3a. And on x-axis we need to find out, so we can say for x-axis our y coordinate will be obviously equal to 0. Thus we can write our potential V will be equal to Q upon 4 pi epsilon naught, and we can write this as 1 upon this is 3a minus x whole square, and this is minus 2 upon 3a plus x and whole square. 1 second. Here I forgot to put square root. So let me write this as 1 by 2 and this also over 1 by 2. So therefore now this two terms cancels out. Now it's the correct one. And this is for our x is greater than minus 3 of a but less than 3a. So first of all, let us write for x is equal to, or not equal to, but x tends to minus of 3a. X tends to minus of 3a. This gives us the voltage V is going to tend towards minus of infinity, and when x tends to plus of 3a, our voltage is going to tend toward plus of infinity. And let's find out the point where this potential is equal to 0. So we can say V is equal to 0. So we can just easily sort it out. The V is equal to 0. This comes as 3a minus of x minus 2 3a plus x is equal to 0. This gives us 3a plus x is equal to twice 3a and minus of x. So from here we get this as 3a plus of x is equal to 6a minus of 2x, and this comes as minus of 3a is equal to minus of 3x, which gives us that our x is equal to a. So our potential V will be equal to 0, then our x is equal to a. Now we can write it for second part, that when our x is greater than our 3a. So if x is greater than 3a, we can write the potential equation, that is our V will be equal to Q upon 4 pi epsilon naught, and this get 1 upon x minus 3a minus 2 upon 3a plus x. And similarly, we can find out the point V where the potential will be equal to 0. So we can say V will be equal to 0. From here we are going to get our x will be equal to 9a. And finally, our third part, that our x is less than minus of 3a, and which gives us that our V is equal to Q upon 4 pi epsilon naught, and we get the equation as 1 upon 3a minus of x. This comes a minus of 2, and this is minus of 3a and minus of x. Therefore, we can summarize it that our V will be equal to 0, and this will be only possible if our x tends to minus of infinity. So we got the necessary, you can say, values, and we can just make a sort of table for them. So for the first case, we said that at x is equal to 3a, we get V is equal to plus of infinity. At x is equal to minus of 3a, we get V is equal to minus of infinity. This was our second. Third, we found out that for our x less than minus of 3a, we get V will be equal to Q upon 4 pi epsilon naught, and that will be 3a minus x minus of 2, and this comes as minus of 3a minus of x. And our fourth point, we found out that is a minus of 3x less than 3a. The expression for our V is equal to Q upon 4 pi epsilon naught, and this comes as 1 upon 3a minus of x minus 2, this comes as 3a plus of x. And this was our fourth one. And finally the fifth one, for x greater than 3a, we get our V is equal to Q upon 4 pi epsilon naught 1 upon x minus 3a minus of 2, and this comes as 3a plus x. So it means, and we also found out that our potential will be on the x-axis will be 0 when x is equal to a and x is equal to 9a. So we can just draw an approximate, and the potential will be 0 at 2 points, that is at a, and another one it is about 9a, and rest it is going to asymptotically will be moving towards infinity. So it will be coming something like this here as well as, and here also something like this, and here also it will be moving like this, and this is for this point is our minus of 3a. So this is approximate graph for that. And finally we have to find out what is C part. If the particle Q starts from rest at the center of circle, show that it eventually crosses the circle. Okay. So the charged particle is going to start with a center that is from this 5a. So you can say part C. And part C, the plus Q charge starts from the point that is 5a 0. And let's find out what will be the potential at x is equal to 5a. So you can say potential at the center which is basically at x equal to 5a, because y will be automatically 0, and we can write that equation that v will be equal to q upon 4 pi epsilon naught. X is equal to 5a, so this comes as 3 minus x, sorry, not 3 minus, 3a minus x. So we get this as over 2a minus, and this comes as 2, and this will be minus minus plus, and this will be coming as 8a. This comes as q upon 16 pi epsilon naught times a, and which is obviously positive. But we know that the potential at the potential on the circle is 0. You can say, but potential on the circle is 0. Okay. So potential at the center, let us call this as Vc, and at the on the circle, let us call this as V0. So by making comparison, we can say our Vc is greater than our V0. Okay, so it means the particle is going to cross the circle. So we can say particle will cross the circle. And it is also asked, I think, find the speed. Okay, for the in order to find out the speed, we can just use the conservation law, that the energy at the center should be equal to energy on the circumference. So we can say that energy at the center should be equal to energy at the circumference, and energy basically is our kinetic energy plus potential energy at the center should be equal to kinetic energy plus potential energy at the circumference. kinetic energy at the center is 0. So this comes as 0 plus potential energy is the you can say the energy because of the minus 2q and because of the plus q. That is nothing but the difference between the two energies, that will is coming as q multiplied by small q 2a minus this is 2q q upon 8a will be equal to, suppose the velocity is v, so this comes as half v square plus energy will be equal to q upon 6a minus 2q upon 12a, and we need to find out the velocity. Therefore we can say that our half mv square will be equal to, we can take q as k as common, so this is our, or we can also take this q as common, a as also common, so this goes by, sorry, this is about 2, this goes by 4, and here also this goes by 6, and we can write this will be equal to our 1 upon 2 minus 1 upon 4, this will be minus 1 upon 6, and this will be plus 1 upon 6, and we take q upon a as common, and this will be minus and this will be here minus. Okay, and these two terms cancel out, therefore we get this will be equal to 4 will be LCM, and this will be our 2 minus 1, that will be 1. Okay, so it can be a positive, so this will be k q upon a, and this is 4 is LCM, so this comes as half m v square, and this 4 goes by 2, we get from here that our velocity v will be equal to, we can write this as k capital Q small q and 2ma. This is our velocity at the exit of the circumference. Next question, it was asked in the 1992, and it states that two identical thin rings, each of radius r, are coaxially placed r distance apart. If q1 and q2 are respectively the charge uniformly spread on the two rings, the work done in moving a charge q from the center of one ring to that of the other is, and here we are given that we are having two rings, so we can just draw an approximate figure for that. So they are coaxial, so let us suppose this is their axis, this is your first ring and this is our second ring. Okay. And they are identical, so let us call this a ring 1 and this ring as 2. Radius is, both the rings is given as r. Let us suppose this is our O center and this is our O prime. And the distance is also between the two is given as r. So this distance between the centers is also given as r. So let us join this point and we call this a distance at d. Okay. And we can easily find out our d. this d will be equal to our, this will be our radius. So we can say our d square is equal to our r square plus r square. Okay. So we can say our d will be equal to square root of 2 multiplied by r. So this is the distance between the center of one of the ring and the, you can say, any point. This point, let us call this as point as A on the other ring. We can just draw on the other side also, but doesn't matter. And we are given the charges on the first ring is given as Q1 and the second one is given as Q2, and it is uniformly distributed. Okay. So in this case, we are going to find out the potential at the center of ring 1 because of charge Q1. Then we are going to find out the potential of the ring R1 at its center because of the charge Q2. And similarly for the other side also. So you can say potential at the center of ring R1. Potential at the center of ring R1. So for the first, we are going to find out due to its own charge. Due to its own charge Q1. And let us call this potential on ring 1 because of 1, which will be equal to K Q1 divided by R. Next, we can find out due to the charge on ring 2. So you can say that due to charge Q2 on ring R2, and we can call this as V12. So V12 will be equal to K charge Q2 and the distance between the two, and the distance between the two is our D. Okay, and D we just calculated, so we can say our V12 is equal to K Q2, and we just found our D is square root of 2 multiplied by R. Therefore, total potential at the ring at the center of ring R1. So we can say that total potential at the center of ring 1, let us call this as V1. Then this V1 will be equal to V11 plus V12, and V11 is our K Q1R plus 12 is K Q2 upon square root of 2 multiplied by R. And similarly, we are going to sort it out for ring 2 also, same method. So you can say the potential at the center of ring R2, potential at the center of ring R2, if that is given as V2, so there is no need to calculate, we can just write it that V2 will be equal to self potential, that is only because of the charge Q2, and divided by, you can say, sorry, not divided by, but because of ring 1. So we can write this as K Q2 upon R plus K Q1 upon square root of 2 multiplied by R. Now we can find out their potential difference. So we can say potential difference between the center of two rings. Potential difference between the centers of R1 and R2. Let us call that as delta of V will be equal to V2 minus V1. And we already know, we simply substitute the value. We get this is K Q2 upon R plus K Q1 square root of 2R minus K Q1 upon R plus K Q2 upon square root of 2R. K upon R we can take common throughout. So this comes as K upon R, and internally we are left with this Q2 minus Q1 plus Q1 upon square root of 2 minus Q2 upon square root of 2. And here Q1, Q2 we taken common by changing the sign, and this will be equal to K upon R. We have this as Q2 minus Q1, and this will be equal to we can take this will be our LCM and square root of 2. 1 second, let me check. This is Q1, this will be Q2 minus Q1, and we get this as 1 minus 1 upon square root of 2, and we can take its LCM. What is the format? Okay, you can keep it like that only, we will sort it out later. Let me solve this here only now. This comes as K upon R Q2 minus Q1 and square root of 2 minus 1 divided by square root of 2. Work done. Work done will be equal to, this is our it will be coming as we move charge Q, and this will be K and Q2 minus Q1 and square root of 2 minus 1 divided by, we have here R and square root of 2, and K is our 1.4 pi epsilon naught. It is K or what? Okay, we can substitute it. So K is our 1.4 pi epsilon naught. So this comes as 1, and this will be our 4 pi epsilon naught. So this is our work done, and we get this as 4 pi Q1 minus Q2. Okay, here it is Q1 minus Q2, and I have written as Q2 minus Q1. So I will just change it. So we get this as Q1 minus Q2, 1 minus square root of 2 divided by 4 pi epsilon naught square root of 2 multiplied by r, and this is our work done. So we get that option number B is the correct one. Option B is correct. Next question. And it states that it was asked in the 1992, and it states that a charge Q is uniformly distributed over a spherical volume of radius r. Obtain an expression for the energy of the system. Assume the earth to be a sphere of uniform mass density. Calculate this energy given that the product of the mass and radius of earth is 2.5 into 10 to the power 31 kg per kg meter. Part B, what will be the corresponding expression for the energy needed to completely disassemble the planet Earth against the gravitational pull amongst its constituent particles? And part C, if the same charge Q as in part A above is given to a spherical conductor of the same radius r, what will be the energy of the system? So we start with part A, and we need to find out the energy of the system. And okay, so we know that you can say electrostatic potential energy of a uniformly non-conducting sphere. You can say that electrostatic energy, potential energy of a uniformly non-conducting sphere that is our U is equal to, this is given as 3 by 5 1 upon 4 pi epsilon naught and Q square upon R. And if we draw a analogy for a in terms of gravitation of a uniform sphere, then we can modify this equation. So we can say that by analogy, our mass is given as capital M and radius is given as capital R. Gravitational constant is our capital G. Gravitational constant is our capital G. Therefore, using the analogy, we can replace our 1 upon 4 pi epsilon naught by G, and our Q square will be replaced by our M square. Therefore, we can say our U gravitational will be equal to minus 3 upon 5. This comes as G M square upon R. because here the sign will be negative because we are talking about disassembling. And from here, if we are only interested in magnitude, then we can say that our energy E will be equal to the magnitude, and this will be equal to 3 upon 5 G capital M square upon R. And we already know all these values, and we also know that our small g is equal to gm upon r square. So we can say our gm is equal to g r square, which gives that our u is equal to minus 3 upon 5. This will be coming as mgr. Therefore, if magnitude, then we can say our energy required will be equal to 3 upon 5 mgr. And we substitute because product of m and r is given to us. Therefore, we can say E is equal to 3 by 5. G, let us suppose taken as 10. Product is given as 2.5 into 10 to the power 31. So we get this energy E is approximately equal to 1.5 into 10 to the power 32 joules. Now we come to the part B. Part B, it says that it is in the form of a complete dissociation among its constituent particles. So you can say that when a total charge Q is placed on a conducting sphere of radius r. So we can say the electrostatic potential energy will be given as U is equal to half, and this comes as 1 upon 4 pi epsilon naught and Q square upon R. And we can write that, or we can also say that our C is equal to 4 pi epsilon naught times R. Therefore, we can say our U is equal to half Q square upon C. Therefore, the total energy that is where U will be equal to 1 by 8 pi epsilon naught Q square upon R. And obviously this is less than the energy stored in a non-conducting sphere. This is less than energy stored in a non-conducting sphere, which was our 3 by 5 1 upon 4 pi epsilon naught Q square upon R. And finally, we can solve for the energy, and with respect to the electric field, so we can say that our energy stored in the electric field that is our small u will be equal to half epsilon naught E square, and there will be two regions for this. One will be inside a uniform charge sphere. First part will be inside a uniform charge sphere at a distance small r, which is less than capital R, where capital R is the radius of the sphere. So the electric field of E is equal to 1 upon 4 pi epsilon naught, this is q upon r square, small r upon multiply by capital R. We substitute it, so we get our u, that is our energy, will be equal to our half epsilon naught, and E is our q small r divided by 4 pi epsilon naught, and this comes as our r cube and its whole square. So we can say our u will be equal to q square r square, this is 32, and this comes as pi square epsilon naught square and r raised to power 6. Therefore, the total energy inside the sphere inside the sphere, and we can call that as our u1 will be equal to integration from 0 to r, and this comes as u multiplied by dv, and u we just found out, so this comes as 0 to capital R q square r square divided by 32 pi square epsilon naught square, this is r6, and the volume will be 4 pi r cube, so dv comes as 4 pi r square multiplied by dr. And now it is simple integration. We get our u1 will be equal to q, and this comes as our 8 pi square epsilon naught r6 integration 0 to capital R, and this comes as r4 and dr. So this will be equal to q upon 8 pi square, one second, epsilon naught was, epsilon naught square cancel out, so here there won't be any square. Now it's correct. Pi square epsilon naught r raised to power 6, and this comes as r raised to power 4 plus 1, that is 5, so this comes r raised to power 5 divided by 5. So we get that our u1 will be equal to q square divided by, this comes as 8 and 40. We have this as square epsilon naught, and this will be capital R. So this is our U1. Now we come to the outside of the sphere. Outside the sphere, which basically means this R is greater than capital R, and we know that the electric field will be equal to 1 upon 4 pi epsilon naught. This will be Q upon small r square, and from here we can write our energy U will be equal to 1 upon 2 epsilon naught and electric field square, that is Q square upon, we get this as 16 pi square epsilon naught square, and this comes as r raised to power 4, and here epsilon naught and square goes away. Therefore we get our U is equal to 1 by 2 q square upon, this comes as 32 pi square epsilon naught and r raised to power 4. So total energy outside the sphere. Total energy outside the sphere. We can call that as our U2. U2 will be equal to, from R to infinity, this comes as U dV, and from R to infinity q square 32 pi square epsilon naught and R4, and this once again comes as 4 pi r square multiplied by dr. Yes, here I missed this also. This goes by pi, and there won't be any pi square. And here also this square goes with pi, and we get this as q square and goes by 32. This goes by 8. So we get this as 8 pi epsilon naught integration r to infinity dr upon, this goes by square and we are left with 2. This comes as r square, which is equal to q square upon 8 pi epsilon naught. This will be minus 1 upon r small r. This is r upon infinity. So we get our U2 will be equal to q square 8 pi epsilon naught times r. So total energy will be U1 plus U2. Total energy stored, that is our U is equal to U1 plus U2. We substitute U1 and U2, we get U, and U1 was our q square 32. U1 was our q square upon 40. So we take common as q square upon 40 pi epsilon r plus q square 8 pi epsilon times r. This gives us q square upon pi epsilon r. Common, we get this as 1 upon 40 plus 1 upon 8. So we get u will be equal to 40 and this is 8 plus 36, 240, and 240 gives us 30 plus 6. So we get this as 36 upon 240 q square upon pi epsilon r, giving us u is equal to 3 by 20 q square and pi epsilon r. So I think this was the, yes. So this is the total energy of the system. I think, yeah, this. Yeah, so this completes the questions which was asked in the year. Total question was 7 and they were asked in the year 1990, 91 as well as 92. So this completes all the 7 questions. Thank you.